So welcome back, everybody. And the topic today is to try to, first, we're going to have a quick review of what we did last week. But then what I wanted to do is actually to give you some of the mathematical details behind the importance sampling. Now, the importance sampling part is actually something which involves a lot of mathematics about the transport theory, diffusion equations, etc. So we will try just to give you a kind of overview of it, because there are lots of mathematical small details and calculations which we often just will state. But I hope you will see the connections between these ingredients, which we called the Langevin equation, the Fokker-Planck equation, and there is some underlying theory on how you solve the diffusion equation, and you obtain the so-called Green's functions. Have you encountered that in courses in mathematical physics, the Green's functions? Okay, yeah, you've met it. But I'm going to remind you of those, because you can solve analytically the diffusion equation when you don't have this drift term. But you can also solve it analytically if you have the drift term. And I'm going to show you how you can do that. So there is some mathematics here which we are going to dive into. And actually, if you now go to the, I have prepared some additional slides. So if you go to the doc folder, just let me point to that before we move on. So if you go to the hub folder where I published the teaching material, and you go to this week, and the thing is that under the PDF files, I made the PDF files a little bit, it has some additions here. There's a whole thing which is called diffusion PDF here. So that file, it's a PDF file, contains a lot of the derivations. So that gives you some of the background material concerning the mathematics of solving the Fokker-Planck equation and the links to the Langevin equation and how they actually, where they come from. So we are going to spend some time today on the mathematical and computational details. And just to give you a quick review of what we did last week. So this was a kind of top-down view. And I like to do this normally because then we can discuss in more detail the kind of, how to say, things which you need to implement numerically. So the equation which you end up looking at is the so-called Fokker-Planck equation. And this is going to give us a way to sample the points by following the distribution which we're using, which is now in our case, the wave function square. So in importance sampling, one of the central equations which is being used for updating the points is the so-called Langevin equation, which then you can think of this as a force which acts on the particles. And then there are some random fast correlations which act at a time scale much larger than the applied external force. So this is nothing but a rewrite of Newton's equation. So you have the time derivative of position. So this is the velocity, which is comparable with a drift term here. And then you can integrate this one up, and then you get an equation for the update of the new positions in terms of the old ones. Then times this force, this drift force, times some delta t, plus some random correlations here. So these are the equations which we end up implementing. And the thing which we discussed last time, and this is actually just some simple derivations, you can show that this quantum force, as we called it, is given by 1 over the wave function multiplied with the gradient of the trial wave function. Now, this makes life complicated when we are going to look at more complicated trial wave functions. In particular, if you have a dependence on the interparticle distance, because then the derivatives, I mean, it gets more complicated to calculate the derivatives, but still calculating the derivatives is, well, I shouldn't say straightforward, but it's also something which we normally leave to automatic differentiation. Now, next week, when we are going to wrap up this stuff, we are also going to look at some computational issues on how we can compute these quantities here in an efficient way. So now when we are dealing with the wave function, we are just dealing with a trial wave function, which is much simpler, which is just a product of harmonic oscillator wave functions. And that makes the calculation of this gradient here quite easy. So keep in mind that this is a gradient. And when you're then calculating quantities, you need to just remember that. And here, what we have is the expression which we need to calculate when we now are updating the Metropolis algorithm to an algorithm where we have a term which will now is going to be interpreted as the probability of moving from x to y in a time step delta t. And I'm going to give you the links here mathematically between this interpretation here and the Fokker-Planck equation, and why we can interpret this quantity as a transition probability. So there are some steps in transport theory, the theory of the diffusion equation, which many of you probably have not seen. And these are the kind of steps I want to give you today. Then, when we have this function here, we can then calculate this ratio. And this is exemplified in that program which we have here. And I just wanted to say a little bit about this program. So the beginning here is just plain notation here, introduction and writing everything to an output file. And here I'm setting up first the trial wave function, and I need to say a little bit about this trial wave function. And I'm also setting up the quantum force. Now, in general, you will have a much more complicated expression, which means that you will often either calculate this numerically, the local energy, by calculating the kinetic energy numerically, or you will use automatic differentiation, which is also a numerical calculation of it. So I'm just going to comment out some of the statements here. And then, so let's just run this one and do that. But then I wanted to say a little bit about this trial wave function, which we are having here. So let's say, so here you see the calculation of the quantum force. You have an analytical expression for the local energy, even though the wave function is a little bit more complicated. So let me just try to switch to the whiteboard and give you a little bit of background for this trial wave function and say a little bit about why this differs somewhat from what you have. So you will recognize the harmonic oscillator argument here for two particles. This is a 2-electron case in a quantum dot. So let's switch over to the whiteboard and take a look at the trial wave function here, so that this is not something which just comes out as a bolt out of the blue. So in this particular example, we have a trial wave function which looks like this. So there's a psi of t. It depends on the positions of particle 1. There is no spin here. And then it has two parameters, alpha and beta. Now, the wave function is given by an ansatz, since these are 2 electrons in a harmonic oscillator trap. So there is going to be a harmonic oscillator here. There is a parameter alpha squared, like the ones you had before. But since we have 2 particles, it's going to be an R1 plus an R2 squared, like that. So this is as you have in project number 1, without the correlation part. Then there is something which we are going to call for J, which is called the Jastrow factor, which is a way to model the correlations. So this part is now something which depends on the relative distance, R12, and it's a function of beta, the other parameter. So this R12 is actually the nothing but the relative distance between the 2 particles. And since we are in a 2-dimensional system, this is simply given by this term here. If you are in 1 dimension, it's x1 minus x2 squared. If you are in 3 dimensions, you would have a c1 and c2 as well. So this is a relative distance. Now, this factor here, the correlation piece, this is an ansatz. And I'm going to tell you a little bit on how you get this ansatz. So this is given by the following function. So it's going to be an exponential, and then there is an R12, the relative distance, of 1 plus beta R12. So what we need, when you think of the quantum force, this is for one of the particles, and that is obviously given by 1 divided by psi divided by t, multiplied with a delta I of psi of t. And this is obviously a gradient, so we have to be a little bit careful when we look at the expressions here. And then let me just check another equation here so I don't say something wrong here. Wait a moment, I went, there we are, sorry. So this has a factor of 2 in front of it. So when you calculate the derivative here, this becomes a little bit more complicated than when you calculate with only the harmonic oscillator, okay? Now, you may ask yourself, where does this term here come from? How can I cook up something like that? So why do I set up a term like that? Now, if you don't know anything about the wave function, there are some constraints about the wave function from the Hamiltonian itself. So let me just give you a very simple example, because this factor which you see here, the exponential of the R12, is something you can extract from the Hamiltonian. So let's look at how we can do that. Now, if you think of the hydrogen atom, this is a much simpler example. And suppose now that we look at only the radial degrees of freedom. Only radial degrees of freedom. Degrees of freedom. And we assume that the orbital momentum is equal to 0. If we only look at the radial degrees of freedom, then the local energy which we have, and this is just now for one electron only, which is a function of r, and our parameter is alpha, but we're just going to leave that one out just for the moment. So this is actually given by 1 over psi t multiplied with the Hamiltonian times psi of t. This is the local energy. Now, let's now look at the expression for the Hamiltonian, where we only look at the radial degrees of freedom. So you know that the Hamiltonian is actually given, H, is in this case for the hydrogen atom, it's given by H bar divided by 2 times the mass of the electron. And then we have the second derivative, the kinetic energy term. And then we have plus some potential energy, which in our case is just minus, and then it's C divided by the charge here. And then there are some constants in front of Z, which I'm going to just label for gamma here. Does that ring a bell? This is the hydrogen atom. Now, when you then look at the radial degrees of freedom only, so that means that this term here, if we now make a transformation to spherical coordinates, which is a standard way by which we solve this equation, then what we have is that this is going to be equal to minus. And now what I'm going to do is to just leave out H bar and M. So I'm just going to say that all the constants, H bar is equal 1, is equal to M, and this is also equal to this parameter gamma, which is in front. So I just put all parameters to 1. So I've scaled the equation. Now what this becomes in radial coordinates only, I'm going to have minus d of r, like this. And then there is a minus, and there's a 2 divided by r of d dr. And then we have some constants, plus constants, which are the parameters which depend on the angles, which we just leave out now. And then if you look at this term here, when you're going to make the transformation of the second derivative in spherical coordinates, there is obviously a part which depends on the angles, which in our case is the reason why I put this as a constant, because what I am interested in now is the limit when r goes to 0. because this is going to create some problems for us. Do you see this limit here? Because we have a 1 over r here, which diverges. And then we have a 1 over r in the interaction, which diverges. So clearly, if you're going to simulate this equation here, you're going to run into problems. Unless there is a escape route here. And actually, you may remember that the solution of the hydrogen atom, so if you now look at the solution as a function of n and L, is now given by some function which is given by the Laguerre polynomial. And these are functions of n and L, and it's multiplied with e to some parameter alpha times r. And then we have the spherical harmonics, which depends on L and ML, and have the angle dependence. So for the case where we put L equal to 0, this function here is very simple. It's just an isotropic function in space for as function of the angles, and it's 1 over square root of 4 pi. Then the Laguerre polynomial here is just 1 for L equal to 0. And then we are just left with this term times the normalization constant. So the wave function is given by something which goes like an exponential with an argument minus r times a constant. Actually, this alpha, which you see here, is proportional with the Bohr radius. Now, but let's now look at the local energy, because we can, from the expression of the local energy, we can extract a minimal constraint on the wave function. So let's look at that. So even if you don't know anything, you can look at the Hamiltonian you have, and from that one, you can deduce a minimal form of the wave function, which your solution has to respect. So if you now look at the trial wave function which we have, so we have an equation here, which is 1 over psi of t. And then I'm going to plug in minus d of r squared. I'm putting all constants equal to, so this actually has a factor of 1/2. And then there's a minus 1 over r of d dr. And then we have a minus, and then we have c over r plus a constant. And this is multiplied with psi of t. Now, there's one thing which we always assume about the wave function. So when r goes to 0, then we have that the derivatives of the wave function of psi of t are given by some constant. So this is a basic assumption we make for the solutions of a quantum mechanical problem. Because else, if this diverges, it means that your kinetic energy would diverge. So we know that the kinetic energy of an object is finite. So we can infer from the physics that these quantities here, these are conditions which we put on the wave function itself. And you may have seen this when you took a course in quantum mechanics. Does that ring a bell? Okay, so that means that when I take this limit, what I can say then, if I take the limit of the local energy, lim r goes to 0 of E of L, what we see then from these equations is obviously that this one approaches a constant. This one here approaches a constant. So since this approaches a constant, we can just leave it out. This is another constant which comes from the angles. So the terms which become problematic for us are actually these two terms here. So what we are getting then, if we now look at that, this is going to go towards 1 over psi of t. And then I have minus 1 over r. This term here, d dr psi of t, is a constant. And then I have minus z divided by r times psi of t. Now the psi of t, which you have here in the potential term, this one cancels that one. So what I'm left with then is minus, so we want these obviously to cancel each other. So we want 1 over r of d of psi t of d of r. We want that one to be equal to z over r. times, and now we don't have any psi of t. So this simply leads to minus d of psi of t, d of r, equal to minus z, plus c. And we know the solution of that one, right? This is a famous equation, which simply tells us that, so we should actually have, sorry, we should have psi of t because a multiplier, I forgot that one, because here we have actually 1 over psi of t from that equation, which you see here. I forgot that one. So that gives us simply that one, and then we know that psi of t then has to be equal e to the minus z times r. So what you have then from the requirement that you want the local energy to be a finite quantity, you then get a requirement on the wave function. Now, if you plot this in one dimension, so if we plot that in one dimension here, just as a function of x, then we know that this function is going to look like something like this. So this quantity here, I mean this behavior with this sharp end here is called the cusp. So this is actually called the cusp condition due to the Coulomb interaction. So there is a divergence in the kinetic energy, and there is a divergence in the potential energy, which have to cancel each other. Now, when I now go to the two-body part, if I look at this equation here, for the Schrödinger equation for two particles, so for two particles, then there is going to be an equation which is going to be given obviously by delta 1, the first particle. And this is, so let me just write it like this. So I have a h bar squared divided by 2m, and then minus delta 2 is the second particle. And then I have a one-body potential, which depends on xr1. And then there is another one which depends on R2 here, and plus some term which is now given by a constant, which is a Coulomb interaction divided by R1 minus R2. So this is the Hamiltonian when I have two electrons, and this potential U, which you see here, could be the harmonic oscillator, or it could be any other type of potential which confines the motion of the two particles. So in this specific case, which we are looking at in that code, this is given by a harmonic oscillator, where we have two electrons here, and they interact via the Coulomb interaction, which is this one, and they are confined to move in a potential here, which is just a harmonic oscillator with a U of Ri, which in this case is simply 1/2, and then there's a constant times Ri squared. That is the standard harmonic oscillator potential. Now, that equation which you saw in the beginning, this ansatz which we made, so I'm not going to go through all the details, but this ansatz which you see here with this term e to the r12, where r12 is actually this term which you see here, the interparticle distance. That term there comes from us rewriting this one in terms of the central mass motion and the relative coordinate. So you can actually rewrite this one in terms of, you can separate it in relative motion plus central mass motion. The central mass motion, R, is actually given by R1 plus R2. So this is a quantity which will never diverge when we have, because the potential does not include R, whereas the R1 minus R2 here is the quantity, this is a relative distance. And this is the quantity which often causes problems for us. So what you can do then is to rewrite this equation here in terms of one, which is about the relative distance, and one which is a function of the central mass motion. So just separating variables. That's a standard technique. Then what you can do then is to look at the relative distance from the kinetic energy and the term which you have here, because these are the terms which become problematic when the two particles are getting close to each other. Yeah? Yeah? You can define it like that. That is correct. So that would be typically, often you define it by dividing by 2 here. Yeah, yeah. So that's a pretty common approach, to take the divide by the number of particles you have. But the thing is that you can always rewrite the kinetic energy in terms of a part which is defined by the central mass motion and one which is defined by the relative motion. When you do that, you can then separate the relative motion, because that's a problematic case. And when you do this, you will get a form of the solution which is going to go like this, but where now R is the relative motion. And that is normally called the Coulomb-Cusp condition, when two electrons are getting close to each other. So if you are expanding your solution in a harmonic oscillator basis, it will actually need a large harmonic oscillator basis to capture this e to the minus z r term. So you can, based on your Hamiltonian, you can actually come with some minimal constraints on the wave function. So when we go back then, this example which we have in the lecture notes is an example where we have modified a little bit this term, but this term still satisfies the R12 goes to 0 condition. So having this one in the local energy, now the wave function, which we plug it into the local energy, that hinders that you get a divergence when R12 goes to 0. So what you're doing then is to make a wave function where you bake in your physics insights. So your physics insight says that we are moving in a harmonic oscillator. Let's take that. And then we have some correlations here due to the Coulomb interactions. And we want to avoid to have a divergence when the two particles get close to each other. To avoid that, there's a minimal requirement, which you can show then mathematically, has to be given by the exponential with an argument, the relative distance. And that makes sure that you will then cancel these divergences when R goes to 0. So you can replace that for a single particle with this R, which could then be the relative distance between two particles. So there are many such things you can do. And when we come to the interaction in project number 1, there is a form of the wave function which actually guarantees that possible divergences will be cancelled. So we don't have the exact wave function, then we have to make an ansatz. So if we then go back to the Jupyter notebook, I simply just wanted to show you the type of ansatz, how we have baked in these ansatz. So let me just find the right terminal here. Where did my Safari end? There we are. So if we go back to that code which we have, this is a digression, but I wanted to bring it up because it's important for the final project. So what we have done now is simply to bake in the relative distance. And you see now that I have the argument, which is this R1 plus this new parameter beta. And that gives me now my new trial wave function. And then that complicates also the analytical expression for the second derivative, which I have baked in here. So I have an analytical expression, but there is a limit to how for when I will switch to automatic differentiation, because when the wave function becomes much more complicated, you will have many more terms for the derivatives. And then you have an expression, an analytical expression for the quantum force as well. So the next part is simply the Monte Carlo part, which we discussed last week as well. So in this case, what we have is a loop over the parameters alpha and parameters beta. We initialize the old position, the new positions, we just put them to 0. And then when we have a loop over alpha and beta, the variational parameters, we are now setting up the position old, which is now given in terms of a normal distribution. So we replace the uniform distribution with a normal distribution for x and y if we are in 2 dimensions. So you see this loops over the dimensions of the problem. And then I have the old wave function, which is given by the position old and the variational parameters. And then I calculate also the quantum force. Then, when I've done that, these are the preparations. I have initialized energy expectation values to 0. I start the Monte Carlo machinery. And in the Monte Carlo machinery now, I suggest a new position. I'm looping over the dimensions. So I have an outer loop over the particles. So I move one particle at a time. And here I calculate the new position by using this normal variate, multiply with the quantum force times this time step. Then I update the wave function. I get the new wave function. And then when I've done with that, I calculate the new quantum force. And then I calculate the Green's function. And it's only the argument. And you see that I set up the argument between the numerator and the denominator. I calculate the exponential. And then I set up the probability ratio, which is the wave function squared, new one divided by the old one. This is the old metropolis test. But now I have a probability of making a jump from x to y in a time step delta t. So delta t becomes a variable, as we mentioned last time. So with that, if I accept it, this is just a standard metropolis test. If I accept it, I update the old position to be the new one. And the same with the quantum force. I set the wave function, the old one, to be the new one. And then I calculate the update to the local energy. I update energy and energy squared, and then I finally calculate the final averages. And the main part here, now in this case, we have 2 particles, 2 dimensions. We do max variations 10, and then we let this run a little bit, and hopefully something will come out. But it's going to take more time because I have 10 parameters for alpha and 10 for beta. So I'm actually running 100 times. So you see that this one is not very efficient. And it's going to beg for a way to find the optimal parameters, because if you look at the code here, I'm actually running with 100,000 Monte Carlo cycles. And I do this 100 times. So it's not very efficient, because I would like to find a recipe which allows me to find the best alpha and beta with few Monte Carlo cycles. And when I have the best alpha and beta, I'm going to start the big machinery. So that's essentially what I would like to do. The code here, as I said, is not the best way. And this is something which we will start discussing in 2 to 3 weeks, which is called the optimization part. So we are going to introduce a standard optimization with gradient descent. And we are going to use gradient descent to find, with fewer Monte Carlo cycles, instead of looping in a brute force way over alpha and beta, we are just going to start with some initial values. And we know often that the analytical solution with no interaction is when alpha is equal to 1. So we would typically pick, if the interaction is weak, we would then pick values of alpha which are close to 1. And then we would start with that as an initial guess and use an optimization to find the optimal values of alpha and beta here. Now, in our case, life is much simpler because we will run the calculation with only one parameter. And that is in the harmonic oscillator part in project 1. So instead of wasting time like this, because you will also see that the quality of the results is not the best one, because with 100,000 Monte Carlo cycles, you're not going to get very good energies. So typically you would need at least 1 million. So if you do a 1 million times 100 times, this is going to be pretty slow. And you see that it's still running here. So I'm going to bring it back when it's done, and then we can take a closer look at what it actually gives us. But now you will have 2 parameters, and you will have to find a minimum for 2 parameters. In this case here, this brute force approach, you will simply find the minimum by the eye first. But then you could typically take the values and use a minimization scheme to find the minimum point. But let's just leave this one like that and then move back to the whiteboard, because now I wanted to say something about the important sampling which we are doing and where these magic things come from. Okay. So let's switch to that. The whiteboard, and then dive into the more the mathematics of the diffusion equation, the so-called Fokker-Planck equations, etc., etc. So what we have been doing when we introduced this metropolis algorithm is that we are calculating, when we look at the metropolis algo, we are calculating this acceptance probability from moving from a variable x to a variable y, a step position x to y. This is something which we have defined as, let me take that one. This is the minimum of 1 and a quantity which we called q of y of x. And this quantity q of y of x is a quantity which is defined in terms of these transition probabilities of x going to y, and then t of y going back to x. And this is then again multiplied with a trial wave function in the new position, which is y squared, divided by the wave function in the previous position, which is given by x. So the whole question now is that, how do we find this? Now, one way of doing that is to start with a diffusion equation. So let me just give you the result, and then we are going to derive the equation. So the diffusion equation is now you having some probability or some function, t of x and t and dt. And this is given by some diffusion constant times the derivative with respect to x times this function p. This is the diffusion equation, okay? Now, what we are going to show here in the coming machinery is that this p can be replaced by this function t, which we have here, this one. So I'm just anticipating the result. And this function is now proportional. When we look at it, it's going to be a Gaussian, and it's proportional with 1, y minus x, the new position, squared, divided by 4 times d times t. So suppose now that this t, if we now take away constants, so suppose now that this t from going from x to y is now proportional to this quantity here, e to the y minus x squared, minus x squared divided by 4 dt. So let me ask you now, if I take this as my probability distribution for making a transition, if you look at this one, and I bake this one in here, and then I just take the reverse, what do you get then? Just 1, exactly. So here, nothing happens. So if I were to, and this is the first step which we are going to look at in order to link this result which you see here. So there are several small items which we're going to bring in. One is that this diffusion equation which you have here, this has an analytical solution. And that analytical solution, if we are going to interpret that one in terms of a transition probability, this is actually the Green's function, which is a solution to this quantity. So I'm going to show you these basic steps. Then the solution to this equation here, if you're thinking of you interpreting this as a transition probability of going from X to Y, this has an analytical solution where you have some constants, and then there is a standard Gaussian here. So this is going to express a probability of going from X to Y or Y to X. The problem, however, when you just have the diffusion term, is that you get a probability, a transition probability, that when you insert it into the ratio here, it just gives us 1. So this is an example of what we call a reversible transition probability. So the probability of going from X to Y is the same as going from Y to X. So this is actually no help. I mean, we are back to the standard metropolis algorithm, where we simply have this equation here. And this is where the Fokker-Planck equation comes in, where we add a drift term to this diffusion term here, this kinetic energy term. And with that drift term, we can still solve the equations analytically. And that means that we are going to get a modified transition probability, which now, instead of having Y and X only, is going to have this drift force. And with that, when we take the ratios between the two transition probabilities, we will get something which is different from 1. So this is the whole basic machinery. And the equation which we get then, which is the Fokker-Planck equation, links with this Langevin equation for the update of the variables, the positions in our case. So there's a kind of meticulous mechanistic machinery which we keep adding up. So meticulous and mechanistic is just another word for boring. So it sounds like that. I am very fond of transport theory. I always liked all aspects of statistical mechanics. So I'm going to give you, after the break, we are going to look a little bit more about the mathematics and how we get to this equation and how we can modify that one with a Fokker-Planck. So the slides contain some of this mathematical background. There's a lot of stuff which you probably haven't seen before, but my hope is that this guiding your eye gives you the hooks on which you can say, okay, I would like to read more, then you can do that. Because because at the end, we are going to take this kind of practitioner's approach. We are going to implement the equations, but as physicists, we like to understand where the equations come from. So this was a kind of motivation and overarching view. And we will need also parts of the next week's lecture to wrap up this stuff. And next week, we will also discuss the way we are going to implement these different gradients in an efficient way in our code. So after that, we are going to start with the optimization part. So gradually, we will build up a code which is hopefully a code which contains the way you would actually write a final professional variational Monte Carlo code. Okay, so let's take a small break. So what we are going to do now is to try to bring in all this machinery about the Fokker-Planck equation, the diffusion equation, the Langevin equation, and how this links with a probability interpretation. So I know that for many of you, not having had perhaps statistical mechanics, transport theory, and so on, many of these things may sound new, but let me try to baby step you through the basic elements. Now, in the slides, the additional slides on diffusion, on the diffusion problem, which we have online, these are slides which give a little bit more of the mathematics, but I will try to guide you through the reading of those slides. So what I'm going to look at now is just first the plain diffusion equation. So originally, we are thinking of having a probability distribution, P of X, and now I'm just doing this in one dimension. So I just have X and a function of T. And I'm going to replace that one with just a wave function. It could be a wave function, but let me just rewrite it in terms of that. So that means that the diffusion equation, the way we have seen it, is given by a constant, which we just leave unspecified. And then we have this kinetic energy term here. And then when you set up the equation, you have some initial conditions, and you also have boundary conditions. So let's just do that. And then you have a phi of x at t equal to 0. We could just call this for a function f of x. Later, we are going to replace that with a delta function. And that is a case which gives us an analytical solution in terms of this Green's function, which we are going to use a little bit later. And then we could have some boundary conditions. And the typical boundary conditions which we have, suppose this is a quantum mechanical object or an object which doesn't need to be a quantum mechanical one, but we could put a boundary condition like this, that when x goes to plus minus infinity, then this phi of x of t is equal to 0 for all t. Okay? So this is just us setting it up. Now, when you look at the diffusion equation, there is a standard way by which you solve this equation. This is something you may have seen if you took a course in mathematical physics. Does anyone remember what's the standard trick? There's a transformation. Yeah, but there is another one. There's another French mathematician. Yeah, it's a Fourier transform. So that's the standard way by which you transform it, and then you can solve this equation immediately. So if you do a Fourier transform, to k, so instead of going to x, so we translate this into momentum space. So let me just bring up my equations here. If I do that, then what I get is that this phi of x of t goes over to a phi tilde, which is a function of k and time. And this phi of k is now defined as the Fourier transform. So this is for x, for all the domains where x is defined, d of x of e of I of k of x of phi of x of t. And I guess you've seen this before, right? Now, that means that when I make the transformation of the k-dependent part or the x-dependent part, the equation then just transforms into d phi of x of t of dt, and that gives me minus d, and then I have k squared times phi of k of t. Okay, this is something which I'm assuming that you have seen in different courses in math, especially if you're taking a course in mathematical physics. So with the initial conditions, what we have then with the initial condition, what you will get then is a phi tilde of k of 0, and that is equal to this f Fourier transformed, and that is simply d of x of e of k of x times f of x. So that will be the Fourier transform of the initial conditions. And in that case, we are going to get a unique solution to that problem. If you look at this problem which you have here, because this is something which we can solve easily. We just integrate over time, and this gives us just an exponential, and where we have to also multiply with initial conditions. So if I integrate this equation here, this one, and add to this the initial condition, then what I will get then is a solution of the type where we have phi of k of t, which is equal to this initial conditions multiplied with e of minus d of k squared times t. So what we are saying then is that this phi, which if we now want to go back, this is simply given by the inverse Fourier transform. So if we want to go back, now we have the solution. We have solved the differential equation by a Fourier transform, because that makes the equation much easier to solve. is just a standard exponential, which we have to integrate up. And then we know that this is given by k of the domain of k. And this is an integral, which is the inverse Fourier transform. And we have minus I of k of x times phi of k of t. Okay. So that's the solution to the problem. And we could now have as an example, if we assume that this f of x, the initial condition, is a Gaussian. So let's now just look at that as a very simple example, because then we can find an equation which is a little bit more interesting for us. Suppose that the Gaussian looks like this, a simple Gaussian, and that means that we would have to plug that in when we perform the Fourier transform. So, and the Fourier transform of, so we normally write the Fourier transform with an uppercase letter f of e minus alpha squared of x squared. The Fourier transform of that one is something which we can calculate. So this is actually the expression which we had here. So we are calculating this one. And now we are simply replacing this f of x with a Gaussian. And we are Fourier transforming a Gaussian. And this is something which we can look up in different tables over over integrals. And this is given by minus k squared divided by 4 times alpha squared. Now, in our case, this alpha squared is something which we, if we now go back to the equations which we had here with d and t. So in our case, this alpha squared, if we rewrite it, this is going to be given by 4 times d times t. So we have a fixed time, keep that in mind, fixed t. So that means that the Fourier transform of this quantity here, e of minus d t k squared, if you look at that one, if we now go back to what we had here and here, then we can also find the Fourier transform of the momentum representation, and that is given by e to the minus x squared of 4 dt divided by 4 pi of dt. And if I do this in n dimensions, this also simplifies so that the Fourier transform, the inverse Fourier transform of this expression e minus d of k of t, this is k squared. This is simply given by 1 over 4 pi, and then I have dt, and then I simply get n half multiplied with the exponential of, with argument x squared divided by 4 dt. Actually, this, what you see here, is called the fundamental distribution of the diffusion equation. So, because what we have here is essentially us solving the distribution equation. No, sorry, not the diffusion equation. So if you look back at what we did here, given, let's say, a Gaussian as a beginning, as an initial condition, we're actually solving this equation here. And when we now do the Fourier transform, we find a simple expression for the solution in terms of this term here. Now, if we start with a Gaussian, if that is our initial f of x, this is the initial condition. So you could think of you initializing the system as a Gaussian. So the system could then be given by a Gaussian distribution. And then you solve the diffusion equation. And by solving the diffusion equation, you have now the final distribution, which is now going to be given by a Gaussian, obviously, in n dimensions. Or if you're just dealing with one dimension, it's simply this form here. Now you see the change when you now solve the diffusion equation is that instead of u, when we started with this one as initial distribution, we have now a distribution which depends on time. So this is where the time dependence comes in. So that means that if you now have a Gaussian at a given time, you see now that as this diffuses the system, then this Gaussian just spreads out. So if you want to make a quick interpretation, you could now think of, if you're now in one dimension, then your original distribution could be this one. So this is a t equals 0. And then when you move on at the t different from 0, and then it depends on how fast you're moving, then your distribution spreads out. So then it may look like something like this, but still a Gaussian. If you replace this with a delta function, then clearly what you could have then would just be a spike around x equals 0 at t equals 0. And this would still evolve as a Gaussian. You can actually show that. And yeah.
Does this mean that the uncertainty in momentum decreases?
Yes, but the uncertainty in position increases. Actually, this Fourier transform is one of the ways you can show mathematically the uncertainty relation. So I don't know if you've seen that when you did a course in quantum mechanics. So what you're doing now is if you sharply can describe x, then it just spreads out in k. Or if you can sharply describe k, then it spreads out in x.
Do you have an intuitive reason for why that happens?
So think of you, assume now that you have this cup of coffee, right? And you have coffee in it. And this is an equilibrium. And then you put some milk in it. So in the beginning, your milk is concentrated in a specific position. And then after some time, you get this cafe latte-like color of your coffee. And that means that all the milk molecules have spread out through the coffee cup. And clearly in that case, you would have some boundary conditions here. So this could be the boundaries of the cup, right? And after some times, the milk molecules spread out till an equilibrium is reached and your coffee becomes cafe latte. That is an intuitive way of thinking of it. So the milk molecules diffuse through the cup of coffee till you reach an equilibrium situation where the milk molecules are everywhere. Was that an okay physical way of understanding it? And diffusion is actually a process which does not, where the velocity is not proportional to time, but it's actually proportional to the square root of time. So what we have here is something which is known. So this solution which we found on the previous page, this is known as the fundamental distribution of the diffusion equation. So what we're going to do now is actually to make some further manipulations of this equation here. And we are going to bring in the so-called convolution theorem, because you can actually view this as an instance of the convolution theorem. But let me just now see a little bit. Okay. So if you now think of the convolution theorem, let me just bring up that as a small digression here. So if you think of a function y of t, if you're now dealing with continuous functions, the convolution is typically written like this as a function of t, and that is given by an integral over s defined for a specific domain of d of s, x of s, multiplied with w of t minus s. That's the mathematical definition of a convolution. So if you look at this solution which we have, this can now be written out as a function, which is the convolution of f, a function f, times, or not times, but convoluted with a distribution, which I'm going to call for s of n. And I'm going to say what that is. And this is a function of t and x. So this variable s, which I define now, so let me just define this s of n. This is just given by the inverse Fourier transform of this quantity E minus D of K. Let me just correct it a little bit. Times T. So I'm just introducing that. Instead of writing the Fourier transform, the inverse Fourier transform, I just define that in terms of a function S of n. So if you then look at the expression which we set up earlier, if we now look at, so let's just put this in as in a parenthesis here. So if we look at this one, this is the same as when we now plug in what we obtained previously. And then I have an integral over dy of n. And this is now defined for real space, which is n-dimensional. I have this y here. And this is multiplied with this exponential. And if I now plug that in, this is actually given by x minus y squared divided by 4 dt. So if you now look at what I'm doing, I have a original function x, which I'm transforming now, which is the same as f here. And then I have defined this function w here in terms of the probability, but now it depends on both t and s here. So these are variables which don't need to be linked with time. So t here doesn't need to be time. I have a function which depends on x at a given n t here, but then I have a function which I started with in the variable y. So that simply transforms this s of n here in terms of x minus y divided by this time dependence. So the question, what I've done here is simply to use this convolutional theorem. And then I'm looking at my variables. So that means my solution at a given time x and at a position x and a time t. And by using the convolutional theorem, what I have now is my function in a previous value multiplied with this variable here. So this function f of y here could then be the one which we defined as phi of x, or rather y, at t equals 0, just to give you an example. So this f here could now represent my initial condition. So suppose now that this f of x, let's not suppose. Suppose that we have f of x in generic. This is the function at t equals 0. But this is just given by some value alpha divided by pi. So I'm putting up a normalization constant here, and then phi 0 of e to the minus alpha of x squared. So this is a Gaussian, okay? Now, this is normalized. And I'm treating this as a probability distribution. It's normalized. so that when I integrate over d of n of x of f of x for x in space of real coordinates, this is equal to phi 0. So that's a normalization constant. Okay. So what happens then is the following. This function which I'm having, this phi of x of t, when I now use the convolutional theorem, is then given by this phi 0. I have this constant alpha divided by 4 pi squared. This is a normalization constant which I have, and then n half. And this is multiplied with a dn of y. And I have an exponential. And my function is now given by minus alpha times y. So this is nothing but us plugging in this function here, in here. But then I have minus this x minus y squared divided by 4 dt. If you look at this one, does it remind you of something? So let me try to bring up something which you've seen a little bit before, but in a discretized form. So before you start thinking about what this reminds you of, I'm going to bring up the discrete variant of a Markov chain. In that case, we had a function in a position x of I at the time t. And that was given by the sum over all the positions you could be at the previous time, where I had the probability distribution x of j at the time t minus 1, multiplied with a probability distribution w, which then marks the possibility of making the transition from xj to xi. This is how we define the Markov chain. So the new probability distribution has now keeps only track of the previous probability distribution multiplied with a transition probability. If you now look back at what we have here, so instead of having something which is discrete, this is actually nothing but the continuous version of the discrete Markov chain. So if you look at this equation, you have the probability distribution at a given time t in terms of the probability at the previous time multiplied with a transition probability. And here we have a discrete set of positions which the particle can be in, or configurations as we call them. So what we are doing now is simply to multiply. So this quantity which you see here, the first one, is our probability at t equals 0, or a given time t previous. And then we are multiplying this with something else. So if you look at this equation which you have here, we can actually write this as follows. So we have this phi of x of t is now given by this integral over all the points in space for which y is defined. And then we would have a phi of y, like that, because phi of y is the one which is given by this quantity here times parts of the normalization constant. So this is, so I'm replacing this one, f, with phi of y. Then the next term is actually given by a term which I'm calling w of x of y at the time t. So this is the same in our case as when we look at it. It's if we look at this specific function here, let's single it out. Only this one. This is the one which we are looking at. This is now a function which is going to be proportional to a constant multiplied with x minus y divided by 4 dt. So this is a function which will have a constant multiplied with the exponential of minus x minus y. It doesn't matter whether we have x or y first, divided by 4 dt. So this becomes interesting for us now because we can make an interpretation when we have this equation here that this function which we are setting up, this w here, now represents a probability distribution for making a transition from y to x at a time t. So what we're actually doing now is that we are taking the discretized Markov chain and we are simply writing this in a continuous form, which then means that suppose now that we start with an initial value at a t equals 0, then this is now given by the initial distribution, which we often have a model for. In our case, it's the wave function squared. And then we multiply this one with a transition probability. So if we use this machinery, we can then, using the convolutional theorem, we can then replace this one with a probability interpretation of making a transition. So there is another thing which I'm just going to quickly set up. So if you now look at what we labeled as a function s of n here, so we label this s of n as the Fourier transform of this probability. And what we are going to do next is simply to replace this function s of n here with a Green's function. So this x of t is now going to be replaced by a Green's function. And these are things which I'm just going to state, x at the time t and y at the time t prime. And this is also a solution of the diffusion equation. But this is a special solution to the diffusion equation because if I take this equation here at y t prime of dt, then I subtract the second derivative of the function of g of x of t of y of t prime. This is a function which is actually equal to a delta function t minus t prime multiplied with a delta in n dimensions of x minus y. So this is just something which I'm stating. And that means that if I take t minus t prime and I call this for a time step delta t, then I can rewrite this function, this Green's function, which is a solution of the diffusion equation, but where the initial distribution is given by a delta function. So you could think of you starting with something which is a spike concentrated at a given point. So we would have x and y of delta t, which is then when we scale this properly in a given dimension, it's going to be given by 4 pi d of delta t. And then this is going to be to the power of n, the number of dimensions which I have, multiplied. And we are going to change to the next page. So let's just wait till people have been able to write it properly. So this is then multiplied with the exponential. So this is the analytical solution squared divided by 4d times delta t. And this function g of x of y of delta t, that plays the same role as the role of a probability distribution probability of making a transition from a position or a configuration, if we want to be more general, from y to x in a time step delta t. So the fundamental distribution for the solution of the diffusion equation is actually given by this so-called Green's function, which then expresses, you can interpret this as a probability distribution for making a transition from y to x in a given time step. So what we have done now is to connect the solution of the diffusion equation with the Markov chain, and where we interpret the solution to the diffusion equation as a probability transition. That is the solution of this particular equation. Keep in mind that you don't need to have that only because we solved it previously. If we go back, step back a little bit, we did previously solve it for this problem which we have here, where we actually started with the diffusion equation, and then we did a Fourier transform. And then with that one as well, we found the fundamental distribution, which is also a solution of the diffusion equation. Then we can show that if we rewrite using convolutional theorem, we can actually also show that, and I'm not giving you all the details, we can actually show that this quantity here, which can be interpreted again as a probability distribution, can then be viewed as the distribution which represents the probability of making a transition from y to x in a given time step. So this is one of the first elements which is going to bring us to the Fokker-Planck equation, because what we have done now is simply to just solve the Fokker-Planck equation. And if we look at the Metropolis algorithm, if you now look at the equation which we have here for this probability distribution, if this is going to represent this transition probability, we will just have a ratio with x minus y squared divided with x minus y squared. So in a certain sense, then the ratio gives us 1, as we stated in the beginning. So we wouldn't achieve anything at all if we stay with just this equation. And that is where the Fokker-Planck equation comes in. So in this case, it means that if I take the ratio in, so this variable which we called yx, which was then given by the probability of making a transition from x to y. And then we had the wave function squared at y divided by t of y going to x multiplied with psi of t of x here squared. In this particular case, this ratio here, since we are just looking at the solution of the plane diffusion equation, this ratio is actually equal to 1. So in a certain sense, we haven't achieved anything by doing all the mathematics. The reason why I bring this in is that you have seen how you can obtain the fundamental distribution of the diffusion equation, and that this, with the convolutional theorem, can be interpreted as a transition probability. And then we can link it directly to Markov chains. But what we need, and we need actually a modification, which is the Fokker-Planck equation. So what we're going to do then, if we now take this phi of x of t here, of dt, then we have a d of d dx. Then we have the term. So let's now just look at in one dimension, just to make life a little bit simpler. Minus f, and this is multiplied with phi of x of t. This equation here will give us a ratio between the two probabilities, the transition probabilities, which is going to be different from 1. And what we are going to show then, when we solve this equation, and this is what we will do next week. So what we are going to see then is the following. If we do this, and this is where we stop today, is that this Green's function for going from y at the time at x and x from x at the time with a time step delta t, that is going to be given by a factor of 1 divided by 4 pi of d delta t to the power of 3/2. And this is an exponential which now has minus, and then I have y minus x minus this d times f of x, and this is squared, divided by 4 delta dt, like that. And then the ratio between y and x at the time step delta t divided by g of x of y at the time step delta t, this is going to be different from 1. And then this quantity f here, which we put up here, is the gradient of the wave function, 1 over psi t of psi t. So we also need this gradient when we are going to evaluate the kinetic energy, because the kinetic energy is the second derivative of the wave function. So when you calculate the second derivative, you need also the first derivative. So this is where we're going to stop today. Next week, so just to quickly remind you of some of the technicalities here, which I brought up. So if you wish to take a look into it, if you now go back to, let's just find here we are. Oops. Okay, I need to, okay. Oh no, okay. Okay, I will just update that one. That's just a small typo here. Sorry. But if you go back to the folder here, I have these slides, which is called Diffusion PDF, which contain additional information, and I'm going to go through some of that next week. And then after that, we are going to look at the technical implementations which we need to consider when we are calculating the gradients, the second derivative. So I hope you can forgive me for all these technicalities, but I think it's useful to see some of the background which leads to the equations which we deal with in importance sampling. So at the end, you can, in a certain sense, just forget about it and just use the equations and implement them. This is essentially what we end up doing, but it's always useful to have a kind of feeling of where these equations come from. And I know that many of you have not taken a course in statistical mechanics and transport theory and similar topics, but I hope you can follow the overarching arguments. So if we use the diffusion equation, there is a fundamental distribution which we obtain. And if you have a Gaussian, you end up with a Gaussian. And you can also express a transition probability, which is called the Green's function, which is a solution of the diffusion equation as well. And that can be interpreted as a transition probability. So next week, in the first lecture, I'm going to go through the slides and then connect some of the dots. And then we are going to look at the technicalities which we need to consider. Then we have all the elements which are needed for importance sampling. So my hope is that we can, by let's say, the end of next week and the week thereafter, that you all have implemented importance sampling in your program for the non-interacting case. So hopefully within 2 weeks. And then after that, we are going to bring in this optimization part, because as you saw from that code, this is a simple brute force where we loop over all the parameters and we run equally many Monte Carlo samples for each parameter. This is a waste of CPU cycles because we can use optimizations to find the best parameters, and then we will start the big Monte Carlo machinery. with the millions and millions of Monte Carlo cycles. And when we have that, then we have the optimal values. And with the expected mean value, we can start calculating the standard deviation. And that leads to resampling methods, which will be the next topic. So there's going to be an optimization part, which essentially is us implementing a Newtonian method with gradient descent as the simplest possibility. And then there's going to be a resampling part where we are going to try to use the results to find the best possible approximation to the standard deviation. So in Monte Carlo calculations, the standard deviation is actually one of these holy grails. So you're tuning and doing this important sampling in order to get a much better standard deviation, which ideally should be as close to zero as possible. So there are going to be two big elements which are coming, which will then add to our code the elements which we need to have a almost professional Monte Carlo code. So optimization and the resampling techniques. And some of you have encountered that when you took a course on machine learning, because you have probably heard about blocking, no, not blocking, but bootstrap, jackknife, cross-validation. We are going to look at a method which is applicable to huge data sets, which is called blocking. Okay, so I'm going to stop here.